All right, today we're going to talk about section 9.3. We're going to talk about hypothesis testing for a mean. And so what has changed? What is different about this section versus section 9.2? And so what's happened here is that the variable now is quantitative. And so it's producing numbers, the variable, and it's no longer producing categorical data. So when you have categorical data, how are you going to analyze that? Proportion, percentage, right? How are you going to analyze quantitative stuff? Means, right? So that's why we're switching over to mu. And so that's what I said there in basically line number 3. Okay. So let's go through the 5 steps. And so you got your hypotheses. So again, the parameter that we're going to be throwing in the hypotheses, the null and the alternative, will be mu, not the population proportion p. And so here, the null hypothesis will be mu is equal to some value. We'll have to figure out that value in the problem. And that some value will be mu sub 0 in the problem. Okay, mu sub 0. And so whatever this value is, that'll be mu sub 0. All right. The alternative, we'll have to figure out to put either greater than, less than, or not equal to sign. Again, we'll have to figure that out in the problem. But it'll be the same value that we threw in the null hypothesis. Step 2, verify your conditions, or if you have any assumptions. So unlike the population proportion p, the conditions are exactly the same as a confidence interval for mu. Okay, so if you recall with the population proportion p, there's slightly different conditions with regards to a confidence interval and the hypothesis testing. Well, the good thing here for mu, they're exactly the same for confidence intervals and hypothesis testing. There's no difference. So I'll just remind you of those things. So the data are obtained using a random sample or an experiment. That's the first condition. The second one is that data does not have any extreme outliers. In practice, we would take a look at a histogram here. We're just going to basically assume that, because if it did, we wouldn't know how to handle it anyways. And so we're just going to assume that we don't have any extreme outliers. And 3, the sampling distribution of x bar follows approximately a normal distribution, aka the sampling distribution of x bar follows a t distribution. Remember, the t distribution is an approximately normal distribution. Okay, and if you recall from chapter 7, there's 2 ways that can happen. Either we need x to be normal, and that's important if you have a small sample size, if n is less than 30. Because what happens if n was greater than or equal to 30? What applies? The central limit theorem would apply then. Okay. So if we wanted to have this condition, we would say in the problem that x is somehow normal. Okay. If either one of these applies, what happens is the sampling distribution of x bar is approximately normal, and we can then use this particular test statistic. Okay. So now, what does the test statistic say? It says, all right, how far is x bar from the value in the null hypothesis in terms of the number of standard errors, which is this number down here. Now, I want to point something out to everybody, is that there's 2 division signs here. Okay, there's a division sign here, all right here, and there's a division sign also in the denominator. All right, so a lot of times I see students multiply s times the square root of n. No, it's s divided by the square root of n. So please pay attention to that one. When we actually work through a problem, I'll show you some steps there, how to put it into your calculator. Step 4, your p-value. So again, it describes how unusual the data would be if the statement and the null were true. All right, and here's the problem: is that before we have any problems, we have with the t-distribution, you have to have degrees of freedom, right? It's a function of the sample size, all right, and it's n minus 1, still the same as it was with confidence interval. Now, here's the problem: is that with the t-table, all you can do is estimate the p-value. Okay, so with standard normal, that was one table and is pretty specific, got into some details there. And so we could look up the p-value using our table. However, when you do your homework in WebAssign, you will need to enter an exact p-value. And so we're going to use StatCrunch to do that. Now, for the test, if we want you to continue with the hypothesis test, we'll just give it to you. We'll give you the p-value for this t-test, okay, when we're testing mu, okay. This is what we call a t-test, by the way. And so we'll just give you the p-value on the exams so you can continue on with the test. But for homework, you can look it up on the computer, all right. then your conclusion is the same as it was with population portion P. You always compare the p-value to alpha. If it's less than or equal to alpha, we're going to reject the null. And we have strong evidence that the alternative is correct. If the p-value is greater than alpha, we would say do not reject the null. We would say we do not have strong evidence or sufficient evidence or statistically significant evidence that the alternative is correct. Okay, so no difference there. All right, there's the 5 steps. Okay, some things have changed, but it's the same 5 steps, which is good. All right, so here's a specific problem. So a medical researcher, after several years of general observation of her patients, thought that it was possible the mean temperature of all healthy humans is actually less than the 98.6 degrees Fahrenheit that we typically use. Okay, so she takes the temperature of 81 randomly selected healthy humans and finds that their mean temperature is 98.5, the standard deviation of 0.3 degrees Fahrenheit. Test her claim at a significance level of 0.05, so basically 5%, right? So let's talk about the particulars here. So what's the variable? What's varying from person to person? Temperature of healthy humans. That's a number. It's quantitative. Quantitative stuff you're going to use means to analyze, and so we're going to look at mu. What's our sample? 81 healthy humans, and so that's right up here. So it takes the temperature of 81 randomly selected. All right, there's our sample size, n. So that means our degrees of freedom is 80. That means our population is all healthy humans. If we looked at 81 healthy humans, that means our population is all healthy humans. Our sample mean is turned out to be 98.5, so she takes the temperature of 81 and finds that mean temperature is 98.5 and the standard deviation is 0.3, which takes us into the next one. What's that? That is the sample standard deviation S. Okay, so sample standard deviation is 0.3. And the significance level here, alpha is set to 0.05 or 5%. So there's the background information, and we should be able to take this information and go ahead and apply it to formulas and so on and so forth. All right, step number 1, state the hypotheses. So we would start with the alternative, right? And I probably should have not brought that up yet. I should have probably just had you think about it, but here it is. She thinks that's possible that is actually less than 98.6, right? So mu being defined as the mean temperature of all healthy humans. You know, we could actually write out those words. We could actually write out the mean temperature of all healthy humans instead of saying mu, but we're just having mu stand for something, okay? So we don't have to write it all out every single time, okay? And so what's the null hypothesis going to be? It's going to be mu is what? Equal to 98.6, right? So that means mu sub 0, this whatever this value is, that's mu sub 0, and that'll be that's what we'll use in the formula to calculate the test statistic. Step 2, okay, confirm the conditions, right? Okay, I think we already said that we took a random sample, all right, and then 2, no mention of extreme outliers, and then 3, since n is equal to 81, remember n was equal to, here it is, n is equal to 81, that means that's greater than or equal to 30. What's applying here? The central limit theorem is applying, and that means the sampling distribution of x bar is what? Approximately normal. It's a t distribution, right? And so we have all the conditions in order to use the formula that we were showing before. So what's step number 3? I'm going to go ahead and calculate the test stat. Well, I didn't mean to have all this pop up at once, but that's all right. So here we have to calculate the test stat. And so what do we got here? We got 81 healthy humans. We have an x bar of 98.5. We have a sample standard deviation 0.3, that's S. We have a mu is equal to 98.6, so that means mu sub 0 is not that 98.6. Okay. So we fill all that stuff in. So we got 98.5, 98.6, 0.3, divided by the square root of 81. So if you haven't gotten your calculator out, get your calculator out, pause this, put that in your calculator. Well, how's this? Before you put it in your calculator, unless you're absolutely sure how to do this, maybe go to the next slide. Because what I did is that here, I said, okay, if you got a TI calculator, be careful. This is how you're going to have to put it in, okay? And so even though it's not shown with parentheses, because this is a minus sign here and the calculator is going to follow the order of operations, we're going to have to put parentheses here. And it would be a really good idea to go ahead and put parentheses also here, okay? So even though it's not shown in the formula, when you put it in your calculator, I'm pretty sure you're going to have to put it in parentheses. And so when you enter it like that, and I think you're going to get your -3 for your test statistic. So try it. Once you got it, come back. All right, p-value. That means we have, so remember our test stat was -3. So here, since we have a left tail test, okay, we're going to figure out the area to the left. Now, why do we have a left tail test again? Because we were testing if mu was less than 98.6. Left tail test, left-tailed, okay? So what we technically got to do, oh, that's a horrible looking straight line, but pretend that was straight. All right, well, that's not too bad. And then here is t-distribution, right? And then we have 0, we have 1, we have 2, oh, I'm sorry, -1, -2, my bad. And then -3. Now there's a little bit more tail in the t-distribution, okay? So I'm going to leave just a little bit of area down here, okay? So technically we got to go figure out that area where you have what? Degrees of freedom of 80. Now, it's really hard to use a t-table to do that, so we're not. Okay, so what I'm going to do, I'm going to get out of this. I'm going to get out of this, okay? And I'm going to go into StatCrunch, okay? So what I want you to do is when you do your homework, all right, and you're ready to figure out the p-value, okay, for for testing mu, okay, what I want you to do, I want you to go to Stat, Calculators, and then come down here to the t-distribution. So Stat, Calculators, t, and something like this should pop up, and it defaults to 10 degrees of freedom. What we want to do is we want to put our degrees of freedom in. Now be careful, don't put n, put in degrees of freedom of 80. And left tail test, so make sure that you got the correct sign. And then here, in this box right here, you're going to put your test statistic. And I would put it to 2 decimal places. Now, we don't have to here because we have 0, 0, right? But I would put 2 decimal places here at least, so that your p-value that comes out here will be what StatCrunch is, WebAssign is expecting. So when we hit enter, notice it goes ahead and gives us a picture there. Kind of looks like mine, and I would just round it to 4 decimal places. And so what do we got here? We got 0.0018. It looks like 0.0018. Okay. So when we go back to our viewing our slides and going back to our slideshow, let's see, from current slide, okay, what do we got here for our p-value? We got our p-value down here. My picture went away, but that's okay. Our p-value is now 0.0018, okay? So what are we going to do? We're going to compare that to alpha. So conclusion. So we got a small p-value, right? It's 0.0018. That provides considerable evidence against the null. Smaller the p-value, more against the null, more for the alternative, right? Certainly less than alpha of 0.05. So what? So what is going to happen? We're going to go ahead and reject the null, right? We're going to reject the null. That means we think the statement in the null is wrong, and the statement in the alternative is what? Correct. And we just got to state that, right? So what are we going to say? We have strong evidence. So when we reject the null, we're pretty sure of ourselves. We have strong. We have sufficient. We have statistically significant evidence that what? That mu is less than 98.6. Well, what's mu in the problem? That is the mean temperature of all healthy humans, okay? And so we're just saying that the mean temperature of all healthy humans, we're pretty sure is what? Is less than 98.6 degrees Fahrenheit, okay? So I got one more problem to go through with you, but I'm going to stop this. I'm going to allow you to think about this, and then once you feel comfortable with this, maybe go to the second example, all right, in the next video. Thank you for your time.